Okay, hello class. Welcome back for the students that have had me last semester. And first thing that we have to get into today is we're going to talk about some mathematical techniques, and then we'll get into a little bit of some of the physics that we're going to be going over afterwards. Uh, I'll try to get a better whiteboard throughout the semester because mine got scuffed up between transport from going home and coming back to school. Okay, so first up, we have to remember some of our derivative rules. So let's do that now. Rules. Okay, so very quickly, for when we're talking about polynomials, we can handle each one of those separately uh, between addition and subtraction terms. But for each one of those terms, you can say that dx of, say, x to the n is going to be equal to nx to the negative, or n minus 1 power. And so a couple things we have to talk about is that the derivative tells us the slope of a function at any point, and a derivative of a constant is equal to 0. So say if we had a constant a here in front, we would just multiply this n by an a, and so then you would get n, or an. So again, in the special case where x or n here is equal to 1, in this case, this is going to be equal to just 1, or if we have a coefficient out front, such as a, then this is just a, either way. Okay, very quickly, we'll have the derivative of the square root, because this could be useful in this class. So the derivative of the square root of x can be rewritten as the derivative of x to the 1/2 power, because that's what our root symbolizes. And so then this is just equal to 1/2 of 1 over the square root of x. For other functions, we'll have, say, the exponential function merely returns the same exponential. And when we're talking about the derivative of, say, this is probably not one that we're going to use in this class, but the derivative where the thing that you're taking the derivative of is in the exponent, then this will yield you the ln of a, or what is being exponentiated upon, times the original function. And one that is a little more common is taking the derivative of ln of x is just going to yield back 1 over x. Okay, trig derivatives. So the derivative of a sine function is just going to be our cosine function. And if there is an extra coefficient inside of our sine function, such as an a or some kind of constant, then we do so let's do the derivative here. And so derivative of the outside function is cosine ax times the derivative of the inside function, which is just equal to a. So this will give us a cosine ax. So we've handled the chain rule here as well as cosine. Now, if you're taking the derivative of cosine, then you will just have that the derivative of cosine of x is going to be equal to negative sine of x. And then the other ones are not too common in this class. Product rule, very quickly, we'll just gloss over this because this is stuff that most of you guys should know. So if you have two functions, f and g, you take the derivative of the first function, so f prime times g plus the original function f times the derivative of your second function g. And that will go ahead and yield your product rule. The quotient rule is slightly different. So say that you're dividing these two. Now this sign here becomes a minus sign, and then you have to divide by the bottom function squared. And then we talked about the chain rule up here. So moving on, let's talk about some integral rules. I know I'm glossing over these, but I want to get to some actual physics too before this is done, or in this video. Okay, so integral rules, and we'll talk about a pertinent example, because you will be integrating in this class quite a bit. So we have this integral here of x to the n, and so then this will give us x to the n plus 1 over n plus 1, and then we have to add c because it's not a definite integral. Okay, a couple constants to remember in this class. These are going to be key constants that you guys should have memorized, and so they are that k is equal to 1 over 4 pi epsilon naught. And epsilon naught in this case is going to be the permittivity of free space. And so we'll get into that a little bit later when we tackle capacitors in this class. But we have simplified our equation here so that you don't have to memorize all of this, and we just have a value for k. And that value for k is going to be 9.0 times 10 to the 9th newtons meters squared per coulomb squared. And now this is a good thing to remember. If you guys can go ahead and memorize the units attached with this as well as the value itself, this will help you in dimensional analysis. And so you can do dimensional analysis on your answers to check your work to see if you have the right units at the end. It's also pertinent to helping us make sure that we have our correct units at the end. Okay, so next we have one thing that may help is if we know about what an electron volt is. So 1 electron volt, or EV, is going to be equal to 1.6 times 10 to the negative 19th joules. So commonly in electronics and electrostatics, we will handle things in electron volts because it's a more pertinent unit for this instead of joules. And so then you can also create a conversion factor between these two to get you the right units that you want. Okay, let's do a little example here, and don't take the math here extremely seriously, but we're going to be very quickly analyzing how we get the potential difference using the force. And so what we can do is we remember from 1710 that F is equal to du dx. And so then here we can say that we know from class that the force is going to be equal to K Q1 Q2 all over R squared. And so R is going to be the distance in between the two charges. And so I just wanted to clarify that if you have two charges and they're the same type of polarity, or like they have, so one is, or both of them are positive charges, then they are going to repel each other. So if two like charges are going to repel, and two different charges are going to attract each other, and that is the rule of thumb. It's like there's a saying that goes opposites attract, so you want to use that saying in order to remember what the force does here. Okay, so going off of that, well, why don't we go ahead and we'll do this. So we'll say that dV here is going to be equal to F dx, and then we'll integrate both sides. And so then this dv is from 1 to 2. And so then we'll have that this is going to be delta v on this side. And then we can substitute in here that this is going to be k q1 q2 and then 1 over r squared dx. And then for this case, we'll integrate over r, as we're just going to be integrating in one direction, r squared here. And so then this is going to give us, and this is between 1 and 2, or a and b. And so then very quickly, we can go ahead and do this integral. And so then if we rewrite this integral here, we can rewrite it as r to the -2nd dr. And so then from here, we can go ahead and say, all right, well, and this is from a to b. And so then this is going to be -1 over r from a to b. And so then you can usually leave it like this. Obviously, you have to keep in your constants from out front. And so this is just letting you know the potential difference between these two charges, or 2 points in space. And so from here, then we can say, all right, well, we can go ahead and we can generalize this to say that this is going to be negative. I guess there's supposed to be a negative out front here. I've left that off. And so then that negative cancels there and we get a positive. And so then this is going to be kq1, kq2 over r from a to b. And so that's how we get our potential difference formula here. And that's how we have obtained it. And the common integrals are mostly just the derivatives that we've done from before, but we do them backwards. Okay, so let's get into some physics now. Okay, so first thing we're going to talk about is the concept of a point charge. So we are going to be taking two charges here, right? And so let's define an axis here like this, and we'll place one charge at the origin. We'll call it 1. And we'll place, say, another charge here on the x-axis here. And why don't we put it just about 1 meter away. And this is going to be charge 2. So all you need to do to find the force in between these two charges is going to be, you're just going to take our electric force, Fe, and K1, or Q1, Q2, over R. So our R is going to be this distance here in between. And so if we go ahead and just say that these are going to be, and then what we can do is we can just plug in what K is. So this is going to be 9.0 times 10 to the 9th. And then there's going to be the units attached to it. They're going to be newtons meters squared per coulomb squared. And as you can see, we have these two constants here are going to be having the units of coulombs here, and this is going to be meters. So those units will cancel out, and this will give us newtons at the end, which is what we're looking for in the force. So let's just say that these are two things of elementary charge. Let's say they're protons, and so then they're going to have the same amount of charge, and we'll say that that is going to be 1.6 times 10 to the -19th. And those are going to be coulombs squared. And so then we're going to have to square this all over 1 meter squared, because when you take 1, you square that, that'll give you 1 again. And so then you can go ahead and run this calculation through on your calculators, say during a homework or exam, and this will give you 2.304 times 10 to the negative 28th newtons, and you can abbreviate this to just 2.3 if you want to take significant figures into account, because our sig figs are going to be 1.6. So there's going to be this is a very, very basic example or a very, very basic problem here of evaluating this. So one thing that can happen with point charges is we can superposition them. So superpositioning charges means you just, it's the same as what we did in 1710 when you superposition forces. So that principle still applies here in electrostatics. So say if we were to add another charge, it would direct the force in a different direction. So, and this is where having positive and negative charges comes in and can be very tricky. So say we added another charge here, and I'm going to make it also 1 meter. So this is going to be 1 meter as well, and this will be charge 3. We're going to give it the same magnitude, but we're going to give it an opposite charge. So in this case, you can see that this force here is going to be, we're trying to examine the charge that 2 has on 1 here, or the force that 2 exerts on 1. So we're going to be showing what force that 3 exerts on 1 here as well. And so as a matter of bookkeeping, what I like to do is I like to keep this negative here, because if you have 2 negative charges, then you're going to get a minus sign, and so that means that they're going to repel each other. And so if you have 1 minus sign and you have another plus sign, you put that together, you're going to get a minus sign. That's going to cancel it, and it's going to be positive, which means they're going to attract. So positive for attract, negative for repel. So that's why I keep this minus sign here. It's just a matter of bookkeeping so that we know which way our forces are going to be pointing. So if we add this third charge in here, our calculation is going to be the same, right? But now it's going to be in the y direction. And now this minus sign here is going to be a plus sign. And so what we can do here is we can see that this charge here is going to be pulling charge 1 up, and this charge will be pushing it away. So our resulting force will be in this direction. Now, since both the charges are an equidistance away from each other, like all three except for these, which you can find the distance between these two charges using Pythagorean theorem by taking 1 squared plus 1 squared. You guys can't see that. Give me 1 second. You guys have 1 squared plus 1 squared, and that will give you 2. And so then this distance here is going to be the square root of 2 when you take the square root of both sides. Okay, so now that we know that this distance is the square root of 2, and so since these forces are going to be the same, or they're going to be equal in magnitude, we know that this force is going to be pointed at a 45-degree angle from the horizontal. That's just some quick math that we can do. If we were to throw these numbers back into, say, the formula for or with the inverse tangent function when we're finding theta, if you remember from last semester, theta is equal to the inverse tangent function of O over A. And when these two numbers are equivalent to each other, theta is going to be 45 degrees. So yes, this is going to be 45 degrees here, and that's something that we can just quickly deduce from going ahead and seeing that both of our forces are going to be equal in magnitude here. So what we can do is you can keep this formula in mind whenever you have to go ahead and actually do this calculation or actually find which way the force is pointing. So this is what you want to do in a case where you don't have equal forces, and they aren't pointed in the same direction, or it's a more complicated problem. Okay. So in order to go ahead and get these, or get the resulting force from these two charges, what we can do is we can just use Pythagorean theorem like we did in this case here. I'm going to erase this here and this here, as well as this. So remember that Pythagorean theorem is c squared is equal to a squared plus b squared. Probably seen that written the opposite way. But so in order to find c itself, you just have to take the square root of both sides. And so in doing that, we can find the force like we did before. So the resulting force F, or the magnitude of F, is going to be equal to f of x squared plus f of y squared. So f of x squared plus f of y squared. And if there is a third dimension, you obviously add on f of z squared, and that'll give you your total force here. So now that we're going to use this equation, we can go ahead and do so. Now both of our forces are going to be the same because they have the same magnitude, because we made it easy in this case. So what we can go ahead and do is we can just plug those in. And so both of those are going to be the same number. So we can just write this as 2f squared because they're going to be the same. So all we have to do is we can go ahead and square this number and then multiply it by 2, take the square root, and that will give us the force. And I believe I've already gone through and did this, except I used different numbers last time. Yeah, I think I did. Oh yes, because I did it on a different direction. Okay, so go ahead and I'll add this as a little quiz problem for you guys. This will be due, let's say by next Monday. I'll add an assignment on your class page, not your class page, but each of your recitation pages, and so this will be part of your participation grade for watching these videos. So go ahead and find this resulting force vector here. And so we've kind of already drawn it out. I've already given you what f of x and f of y are. And so you just need to find the resulting force using the Pythagorean theorem. That should be easy enough for you guys to do. Okay. I hope everybody gets a chance to watch this video, and next week I will be posting another one about expert TA problems. Okay, have a nice day.